Hello, welcome to watch our videos on probability and statistics and subscribe to this channel. In this video, we will talk about binomial and multinomial distribution. So before we go to binomial and multinomial distribution, we first will talk about Bernoulli process. So experiment can be called a Bernoulli process if it has the following properties. So the experiment consists of repeated trials, and the repeated trials are independent, so which means each trial has no effect on the result of other trials in this series of trials, right? And each trial will result in an outcome that may be classified as a success or a failure. So the Bernoulli process, the result is binary, only yes or no. And the probability of success in each trial, denoted by P, remains constant. So let's take a look at an example. Consider a set of Bernoulli trials where 3 items are selected at random from a manufacturing process, inspected, and classified as defective or non-defective. So here, the defective item is designed as a success. So in Bernoulli process, success not means the good or not good. Success is just the result which we are interested in. So usually, for example, for the defective item is the result we are interested in. So we call this is a success. And the number of success is a random variable x, assuming integral values from 0 to 3. And 8 possible outcomes and the corresponding values of x can be listed in this table. So if we list all results of each trial, so it can be non-defective, and non-defective, defective, and non-defective, and so on. So this will list all the possible outcomes of all 3 trials. Then here x means the number of success. So here the success is a defective. So we just count how many defective in each result. Clear, right? So this is the random variable x. So since the items are selected independently, and we assume that the process produces 25% defectives, so we will have, for example, for n dn for this outcome, we can calculate the probability is 3 of 4 times 1 of 4 and times 3 of 4, because the result is n dn. And the probability for this outcome is 9 of 64, right? If we calculate all probabilities for all outcomes and summing these together, we will get the 1 for all possible outcomes probability. So this is clear, right? Because only 1 of these 8 outcomes will occur, right? And similar calculations will yield the probabilities for the other possible outcomes. So the probability distribution of x. So here we focus on the x random variable. The probability is for 0, 27 of 64. For 1, it's 27 of 64, right? And so on. How can we get this probability for x? We just count the probability of these outcomes with the same value of x. So for the x is 1, we count these 3 outcomes probability, we will get 27 of 64, right? So the number of x of success in a Bernoulli trial is called a binomial random variable. And the probability distribution of this discrete random variable is called the binomial distribution, and its values will be denoted by B, X, and P. And the Bernoulli trial can result in a success with probability P and a failure with a probability Q, where Q equals 1 minus P. Then the probability distribution of the binomial random variable x can be denoted as B, x, and P equals a combination of nx times px power times q n minus x power. So x can be 0, 1, 2, 3, 4 until n. So if we want to calculate the different probabilities associated with a specific x random variable during n Bernoulli trial with probability p, then we just fill in this form. So when n equals 3, p equals 1 of 4, the probability of x, the number of defectives, can be calculated as bx3 1 of 4, right? So equals 3x combination 1 of 4 x power 3 of 4, 3 minus x in power. X can be 0, 1, 2, 3. So this form will get actually the result in this table, right? So an example of binomial distribution, the probability that a certain kind of component will survive a shock test is 3 of 4. Find the probability that exactly 2 of the next 4 components tested survive. So the solution is, if we assume the tests are independent, so this will be a Bernoulli process, and the probability for each trial is 3 of 4. So there are 4 tests in total, and we can calculate the Bernoulli binomial distribution's probability of x equals 2, because we want to know exactly 2 here. X equals 2 and n equals 4, and with a p equals 3 of 4. So it is combination of 4, 2 times 3 of 4, 2 power, and 1 of 4, 2 in power. So the combination of 4, 2 equals 4 factorial divided by 2 factorial times 4 minus 2 also equals 2 factorial, right? Then we fill in the form and we get the result is 27 of 128. And where does the name binomial come from? The binomial distribution derives its name from the fact that n plus 1 terms in binomial expansion of q plus p in power. So if we make expansion of q plus p in power, it is n0 combination qn plus n1 combination p1 qn minus 1 until n combination pn. So each item actually is a binomial distribution random variables probability. So when p plus q equals 1, so each item is a probability, right? So this is where binomial distribution name comes from. And odd probability sigma b x n p for x equals 0 to n will be 1 if q plus p equals 1, because q plus p equals 1 once n power equals 1 too, right? So this summation of all items will be 1. Take a look at another binomial distribution. The probability that a patient recovers from a rare blood disease is 0.4. If 15 people are known to have contracted this disease, what is the probability that at least 10 survive? From 3 to 8 survive, and C is exactly 5 survive. So this is actually the binomial distribution of n equals 15 and p equals 0.4. So for the question A, we will calculate the probability x larger than or equal to 10. So which equals 1 minus p of x less than 10. So we note when we calculate the binomial distribution, usually we will find a table, probability table called binomial distribution table. So from this table, we can find very easily of the value of sigma for different values of x with their probabilities in binomial distribution. So in this case, we just find p x less than 10, then 1 minus this item, so equals 0.0338. And similarly for the second question, we want to calculate the probability of x between 3 and 8. So from the binomial probability table, we can calculate this term equals this term x from 0 to 8 with binomial x 15 0.4 minus sigma x from 0 to 2 with a binomial x 15 0.4. So the result is about 0.8779. And for the third question, the probability x equals 5, from the binomial distribution, we can get from this term the sigma x from 0 to 5 with a binomial distribution minus sigma x from 0 to 4 binomial distribution. So the result is 0.859. So another example is a large chain retailer purchases a certain kind of electronic device from a manufacturer. And the manufacturer indicates that the defective rate of the device is 3%. So the question A is, the inspector randomly picks 20 items from a shipment. So what is the probability that there will be at least one defective item among these 20? And the question B is, suppose that the retailer receives 10 shipments in a month and the inspector randomly tests 20 items per shipment. What is the probability that there will be exactly 3 shipments, each containing at least one defective device among the 20 that are selected and tested from the shipment? For the solution A, if we denote x the number of defective devices among the 20, then x follows a binomial with x 20 0.03 distribution, right? So it's quite easy. We just calculate the probability of x larger than or equal to 1. So which means 1 minus the probability of x equal to 0. And this term can be found from the binomial distributions table, this one. Or we can just calculate manually. So the result is about 0.4562, which is at least one defective in the 20 items, right? So for the question B, in this case, each shipment can be taken as an Bernoulli process. So each shipment can either contain at least one defective item or not. So testing of each shipment can be viewed as a Bernoulli trial with probability 0.4562, which we have calculated from the question A. So like this, so we can assume independent from shipment to shipment and denoted by Y the number of shipments containing at least one defective item. So in this case, Y follows another binomial distribution, B, Y, 10, because we want to know in the total 10 shipments, right? So with a probability of 4562, we calculated from question A. So exactly 3 shipments from these 10 shipments contain at least one defective. So this probability is Y equals 3 with combination 10, 3, and with these probabilities power 3, and times 1 minus these probabilities power 7. The result is about 0.1602, which means this probability for exactly 3 shipments during of these 10 shipments contain at least one defective item. And the mean of binomial distribution is NP, and the variance sigma square of binomial distributions is NPQ. So where Q equals 1 minus P. So another example is, it is conjectured that an impurity exists in 30% for all drink wells in a certain rural community. In order to gain some insight into the true extent of the problem, it is determined that some testing is necessary. And because it is too expensive to test all of the wells in the area, so 10 are randomly selected for testing. So the question A is, using the binomial distribution, what is the probability that exactly 3 wells have the impurity? Assuming that the conjecture is correct. And question B, what is the probability that more than 3 wells are impure? So it's quite easy. For question A, we just calculate binomial 3, 10, 0.3 and check from the distribution table which equals the difference of these two parts. And the result is 0.2668. And for the second question, probability of x larger than 3 equals 1 minus this item equals 0.35. And next example is, find the mean and the variance of the binomial random variables of previous example, and then use Chebyshev's theorem to interpret the interval mu plus minus 2 sigma. So the solution is, since example was a binomial experiment with n equals 15 and p equals 0.4, so we have mean equals np equals 6 and sigma square variance equals npq equals 3.6. And taking the square root of 3.6, we find sigma equals 1.897. So the required interval is 6 plus minus 2 times sigma. So which means from 2.2 to 9.79. And Chebyshev's theorem states that the number of recoveries among 15 patients who contracted disease has a probability of at least 3 of 4 of falling between this range. So because Chebyshev's theorem states between the range sigma minus 2 sigma, mu minus 2 sigma and mu plus 2 sigma, between this range, the probability for any distribution is larger than or equal to 1 minus 1 divided by 2 square. So equals 1 minus 1 divided by 4, which equals 3 of 4. So this range's probability is at least 3 of 4, right? So we can say in these cases, the probability of random variable x between these two ranges is at least 4. And we take the integer value because in this case cannot be a real number or real number. So we take integer, we can say between 2 and 10's probability is at least 3 of 4, following Chebyshev's theorem. So now from binomial distribution, we can extend to the multinomial distribution. So a multinomial experiment is actually when we look in a trial like binomial, but in this case, the result is more than 2. So which means if a given trial can result in any one of k possible outcomes, E1, E2, Ek with probabilities P1, P2, Pk, then the multinomial distribution will give the probability that E1 occurs x1 times, and E2 occurs x2 times, and Ek occurs xk times in n independent trials. And the sum of x1, x2, xk equals n. So we show denote the joint probability distribution is f x1, x2, xk, and p1, p2, pk, and n. So this is the multinomial distribution. And probability can be calculated as for the result of x1, x2, xk, these random variables within n total trials is the combination of n x1, x2, xk times p1 x1 power, p2 x2 power, until pk xk power. And the condition is sigma xi equals n and sigma pi equals 1. So we take a look at an example. The complexity of arrivals and departures of planes at an airport is such that computer simulation is often used to model the ideal conditions. So for a certain airport with 3 runways, it is known that in the ideal setting, the following are probabilities that the individual runways are accessed by randomly arriving commercial jets. For the runway 1, probability is 2 of 9, and the runway 2 is 1 of 6, and the runway 3 is 11 of 8. So what is the probability that 6 randomly arriving airplanes are distributed in the following fashion? Runway 1 with 2 planes, runway 2 with 1 plane, and runway 3 with 3 planes. So the solution is using the multinomial distribution. We have the probability for 2, 1, 3 with the probability 2 of 9, 1 of 6, 11 of 8 in the total 6 trials is the multiplication of all these 4 terms. The result is about 0.1127. Thanks for watching.